Okay, so I just left off. I got cut off there last lesson, but now back to creating ionic compounds and then using that crossover rule in order to create those compounds. Here we have calcium and phosphorus trying to create a ionic compound. Okay, calcium phosphorus. If we go to our periodic table, right here we have calcium, which is in group 2. So that will have how many, what's the ionic charge on group 2, on a group 2 metal? Oops. Well, we know that a group 2 metal will have calcium, calcium plus 2. Okay, we'll have a charge of positive 2 because it is in a group 2 metal. Okay, and then phosphorus. Where's phosphorus? Phosphorus right here. Okay, so if we look here, halogen 17, 16, 15, 15 minus 18, which is our noble gases. So we 15 minus 18, so our outer valence electron will have 3. Okay, our outer valence electron configuration for phosphorus will be -3. Using the crossover method, okay, we can predict that the equation will look like, or the chemical formula, calcium phosphide. And remember, every time we have a cation and an anion in an ionic compound, what happens is we take out our ending, okay, and then put I, D, E, and ide in there. So this would be aluminum chloride, lithium oxide, magnesium sulfide. Okay. Now we've done the crossover rule, and we just demonstrated the crossover rule. So that's what these were. That's what we just did. Okay. But I want you to remember as we progress into quizzes and things like that, that ionic compounds should be reduced to their lowest terms. They're always reduced to their lowest terms because they represent a ratio of atoms. Okay, for example, for every 3 calcium ions or 3 calciums, there's 2 phosphorus. For every 1 aluminum, there's 3 chlorine. For every 2 lithium, there's 1 oxygen. Okay, for every magnesium, there's equal parts sulfur. Okay, so it's really important to remember that ionic compounds represent a ratio. Okay, and they always need to be put into lowest terms. Okay, um, I want you to take a look at these three: calcium chlorine, magnesium oxygen, sodium sulfur, and gallium oxygen. Okay, and I want you to try to figure out the chemical equations for these ones, the formula, the ionic compound formula for these reactions. Okay. I'm going to continue on. You can do that on your own time. So if we look at ionic compounds in water, okay, some ionic compounds can dissolve in water. Okay, for example, table salt. Sodium chloride, okay, is really just sodium and chlorine mixed together. We know that sodium, okay, has a positive 1 charge if we go to our periodic table, and we know that chlorine has a negative 1 charge if we go to our periodic table. Okay, and therefore it has a ratio of 1 to 1, 1 sodium for every chlorine. So what happens when sodium chloride or table salt gets put into water? What happens is it disassociates from itself. Okay, so it separates. The sodium and the chlorine separate from each other. Okay, and then they get engulfed, or they get surrounded by water molecules. So water molecules surround each ion as it leaves the crystal, which prevents it from rejoining the crystal. Okay, so for example, we threw table salt right here. You have your sodium chloride crystal right here. It gets dropped into water, and what happens is you get the dissociation of sodium and chlorine. Okay, and the dissociation happens. What happens is the water molecules actually surround each individual atom, not allowing it to bind back to to the crystal. Okay, so that's the thing. However, in this water, there's always going to be one sodium to one chlorine. Okay, same thing for calcium chloride. Okay, there's going to be two chloride ions for every calcium ion produced. So in sodium chloride, you had one chlorine atom produced for every sodium chlorine for every sodium produced. Okay, but for calcium, okay, calcium chloride, you're going to have two chlorine molecules for every calcium produced. Okay, there is a lovely video on physical properties of ionic compounds, but I'll go through them quickly. Okay, so ionic compounds again have several common physical properties. First is they dissolve in water. Okay, that's one. Two is brittle due to their crystalline structure. Okay, so they're a crystalline structure, and these cations and anions arrange in a regular repeating pattern. Okay, as you can see here, you're gonna have your negative positive, negative positive, negative positive. You'll never have like a positive positive together or negative negative together. Okay, so they form these cubes and these crystals. This makes them very easy to break. So if you can smash it with a hammer, and what happens is it just literally snaps right at the point at which the structure at which you hit. Okay, so it can snap at a specific point, breaking off into now two sections. And you can think of that as like a brick. Okay, if I use a hammer to crush a brick, it's not the exact same. Okay, the brick doesn't just like blow up into dust. Okay, what happens is you get a chunk of that brick that breaks off. Okay, it's not necessarily brittle, but it breaks off like that. Okay, they also have a very high melting point. Okay, it requires a lot of energy to break the strong ionic bonds that they form. Okay, if you put a cube of salt into a frying pan, it takes a lot of energy in order to break the bonds between the ionic break the ionic compound down. They conduct electricity when they're aqueous or when they're dissolved in water. Um, you know, it's not the water that necessarily allows for electricity to pass through it. It's the actual electricity needs something to use in order to get from one area to another area. Okay, so it doesn't really use water molecules. It actually uses dissolved dissolved electrolytes such as sodium, chlorine, potassium, calcium in order to travel really fast through water. Okay, because sodium and chlorine dissociate in water, I'm just going to use sodium and chlorine because this is the example here. What happens is lightning can hit or electricity can hit these ions and jump from ion to ion to ion to ion to ion to ion and really conduct that electricity. They do not, however, conduct electricity when they are solid. This is because there is no space in between them, right? So electricity needs to jump from ion, then jump to another ion. When they're too close together, what doesn't allow for that to happen. Okay, an example would be if you did an experiment like this. In salt water, what happens is the dissociation, the electricity can jump from ion to ion, allowing the light to be lit. Okay, and that brings us to the end of the ionic compound lesson. If you have any questions, again, just let me know, and I can take over from there. Take care, guys.